Okay, I think we can start. Good morning, everyone. Now is we have covered the chapter one for most of the part. Basically, chapter one is review on statics. So my expectation is that you can review all the concept in statics, especially if you have time. You can check this exercise I have put in the Moodle. So I put these two exercise. I think we are going to cover these exercises tomorrow. Okay, we are going to solve this tomorrow. But if you have time to solve, please check this out. Okay, this 1 and 2. This is the other one. Okay. Okay. Today I would like to go to another topic, which is it's stress and strain. So let me just explain a little bit what is stress and strain. So stress and strain is basically there are fundamentals. Let me just write here, and then you write this is a fundamental components. In mechanics of materials. Okay. Previously, we have seen how for example, the two-member forces can be extracted. For example, if you have this kind of bar, let me just make it a little bit bigger. Okay, let's say we have a bar here, which have a pin jointed at this point, and this other pin here. This is a B. We call this is a two-member forces, which means that we have 2 points here, which we can. So let's say we have some loads here, which is P, and then we are going to evaluate something between this distance x. So we are going to see how the internal forces works, and I think in the previous course we have this internal forces. Can I say this is equal to x, and we have this is the shear force, this is the normal force, and this is the moment. Okay, this is one way. Another way, we could also see from the other member forces. Which you can also apply, let's say here. Let me just write to describe this is the same member force. And this is practically the opposite side of the other member. Okay, so this will be the normal forces, and this will be the moment. I hope it's clear. Okay. So basically, they are the same value. Okay. So stress concept is going to measure internal force at the end of the day. Okay, internal forces distributions, and strain is going to be about the changes or how the member forms. Member means if we have the bar, we call this as the member. Okay. Okay, now we start from the normal stress, okay, the simple one. So let's say we have this, the process A, B, C, D. So from the process A, this is the undeformed bar. So let me write here, this is undeformed, which basically just a bar with some hole for pulling the bar, and then it is going to be deformed by a forces of P. So we have P, the forces that is applied, and then if we look at this A, the A asterisk means that is the point that is changes. So from A at the beginning to A asterisk. Okay, so it's changing its locations. Okay, and then it is deformed, okay, with the load P. And if we cut open of this A asterisk, it's actually having some such as distributions along this, let's say the area here or the distance here. Okay, and then we could say this is going to be the resultant, the total resultant of all distributions. We can simplify them, right, as FA equal B. Okay. Okay. And the same thing we have on B. We have B. Let's say if we cut open B, we have FB equal P. Okay. Of course, this is going to be measured by the statics environment, right? Okay, so basically, what the stress here is, we are going to see there are sometimes some assumptions that we can make. For example, now here is all these distributions are homogeneous. Okay? They are all the same, so we can simplify and then we could say that if this is going to be rectangular like this, the same force, which means the same force, we could say that the resultant is exactly at the middle. Okay, there will be a different condition if, for example, this distribution here is longer, it's higher, and then it's going to be like a triangle like that. Will be different. Okay, I hope that is the statics. I hope you still remember that. We are going to review a little bit later. So, but what I want to say here is we have some assumptions how to make the bar usually homogeneous, and then there are other several conditions as well. And so basically, stress is defined by the force divided by the area, generally. Okay. So the normal stress, right here, or let me just, I have here already, so let me just move here. So normal stress is the force normal, which means perpendicular to the area. Okay, so if you have the area here, like say this is your area, so this is normal. Okay, it's perpendicular, divided by the area on which the force acts. And then we could write the normal stress as sigma notations. And then XYZ means that if it is in the volumetric space or 3D spaces. And we could take this in terms of limit. Okay. How we read this is actually the whole, let's say we have, let's start from here. I think it's easier. And if we have the random surface like this, or random blocks or shape, and then we define this is to be the surface, okay? And then we cut a small rectangular open here. And of course we have the distribution forces, right? And the distribution forces along this delta A, the more smaller A, the stress will be highest, right? So we are going to get this resultant or the stress if we take the limit of this delta as close as much possible to 0, okay? So that's why we have this R point on the right side of the picture. And some conventions, okay, that is going to be all through the course is positive value or positive stress means, or let me write just stress. Positive stress means it is a tensile, okay? And if you have a negative stress, that is a compressive. Usually, the standard units are Pascal or megapascal, usually megapascal, because megapascal means, so let me just write the whole standard units. Units usually megapascal or Newton over millimeter squared. There are some non-standards like British conventions, which using the PSI or kilopounds per square inch. KSI or PSI. This is kilopounds per square inch if you want to know. The PSI is the pounds. So pounds per square inch. Okay, and then we could write also within this distribution stress, we can write an average value. So basically all the stresses that is explained here, they are basically just F over A. The differences between one of another is just the conditions and how we apply, okay? So since average number of stress is based on the F over A, and that is depends on how we apply the forces, then simply if we are going to just to see here this A and B, then the average, let's say the average for A at point A, we can just simply write the FA over A, or in this case it's just B over A. And since this is the same thing, and we can just write that they are the same thing. This is not B, sorry, it's A area. Okay, now of course, if we are talking just the concept and without an application, maybe it will be a little bit not clear. So let's say we have an example just to apply the stresses and how to compute the forces, or perhaps the area or the thickness on a subject. So let's say we have a crane which consists of boom AC. Oh, this is not kip, sorry. This is not kips. It's 22 kilonewton right here. It's 22 kilonewton. So let's say we have boom AC, and then it has a pin at A, and it has another tension bar BD supported by this BD, and then you can check how the pin on A, this is the view from the top here. So you can see that the pin AA can move, okay? And then this is the pin for B. So if you see from the side, actually from that side, okay, this is the pin. So it has the thickness, okay, thickness T, 13 millimeter. BD has also width of 38 millimeter. If the vertical load at C is 32 kilonewton, what is the average tensile stress at the bar BD? So BD is here with 38, and then thickness is going to be that part, okay, this part. And then it gives you the ratio 3:4:5. This is to get the angle, or to get how we can separate the forces and make it into X and Y component, right? Okay, so what's the first thing we can do? The first thing we can do is we need to make a free body diagram, okay? So the best way we can see the free body diagram works is, where is the extra loads? This one is the loads, right? So at least if you want to make a free body diagram, you need to include this. So I think this will be the better choices, because each one of them already in the component. Okay, this is the big one. It has everything. It has the pin here. It has the pin here. Okay, so let's just make that first. This is C. This is A. And then how we assume the forces on a pin A is basically, we can assume any direction is okay. Okay, as long as we're consistent, and we are going to see whether we are correct the directions based on the value we get. Okay. So let's say, assuming this have reactions, okay, have a force reactions that it has. Let's say this is going to be, let me write with the green color. So it has this AX, and it has this AY. Does it has any moment? Moment here? It can move here, right? So I think only X and Y, okay? That's the first assumption. And then how about this? B. I think let me just write B as let me just write here. So this FBD, okay, that is going to be the one that we are looking for. And then we have the triangle, right? I can make the same triangle here. 3, 4, 5. And then we have, let's say this is the 22 kilonewton. Another important thing is the distance. This is 1.5 meter. Okay, I think every aspect we have done. And then what should we do next? So from the whole perspective of this member or here, we want to calculate this, right? How do we use our equilibrium? What should we use from the statistics? There are only two options, sigma f equals 0 or sigma m equals 0. Okay, if you have f, then for vertical you have this, and you can construct another one here. But you need another process to calculate this one, right? You need to have the x. So I would suggest if you have forces, distance, just use sigma m. Okay? This is something you don't know. This is something you know. You don't know this, right? You need to compute this. So another question, if you use sigma m equals 0, which point you are going to take as a reference, A or C? A or C? Any idea? You can just try. What happens if you use C? If you use C, you will waste your 22 kilonewton that you have known, right? And we need to know this, right? So that's why, rather than C, just use A. This is something that I think we don't really need to know from the questions, right? We can just take this as a reference. So we can use this, or perhaps having this as a component, and then going here, and then this going there, and then equaling all the components equal 0, right? So let's do that and write down sigma m at A is equal 0, and then usually we establish that the rotations here is positive. Actually, if you make your own rule, it's okay. For example, if you say rotations on like to the left is positive, it's also okay, as long your rules consistent through the process. Okay, it's okay. If you sometimes find going to the left is much better, it's okay. As long as you come up consistent, it will be the same. It will be the same. Okay. So let's say this is positive. You just to help calculate. Okay, just to help calculate. So what is the distance is 1.5. Okay, so FB, or let's say starting from the C, so we have, let me write here, 22 kilonewton multiplied by 2 meter. Okay, it's positive. And then what else? The other one is the opposite, FBD1. So minus FBDN 1 meter is equal 0. So FBD is 44 kilonewton. Hmm? 2.5. Should be, let me check. Oh, it's the 3, 4, 5 triangles. I forgot. I skipped the process. Sorry. So should be here. So this will be It's okay? Okay. So it should be this. Should be, let me explain. Okay, should be this. Okay. Let's see what else. What is the question? I forgot. The tensile stress. So tensile stress by definition is just F over A, and we have F is the FBD. And then the area is depends on the width and thickness here, right? So 44 kilonewton. Okay, and then you can calculate. I have calculated before. This is 89.07 megapascal. And since it's positive, this is a tensile value. Maybe just to make sure that it's clear, this is the triangle. Okay. And maybe let me just write here in case you need. Okay, any questions? Any questions? What else do we have here? Right hand rule. Okay. Okay, now we move to the news, another subtopics, which is the stress resultants. So basically, the stress resultant, we have seen before the internal resultant in the introductions, and then the previously we have the average normal stress on the cross sections, right? And there are more greater details in the relationship between the distributed normal stress on cross section and the whole resultant. So if we look back at the definition on the normal stress, now we could replace the delta from before. Before is here, this one here. The delta here, we can replace the delta with d. Okay, in mathematics, d represents something that is really small. So suppose that we have the sigma is delta f delta a, right? And then we want to say that we could replace this and then replace all the delta with d. So df and then dA. And then we integrate all this too. So we get the f of x, which means it will be depends on the independent variable x. Okay, so we could say that our f is actually our integrations from the stress dA or the sigma dA. Okay, and then similarly, what we have on the moment. The moment for this is, let me write here, this is sigma fx equals 0, or the sigma fx, and this is the sigma moment with respect or reference y, and this is sigma moment with respect of z. So the distance will be the z multiplied with f, that will be the moment, and then negative y multiplied with f. Okay, so we are going to see that the resultant of a constant normal stress on the cross section, basically we say that the normal stress that corresponds to axial force acting through the centroid. So I would like to emphasize the centroid here, which means that the centroid, it becomes important in our discussion. So let's say we are going to make this relevant to our calculation. So f of x we can write as, if you get the integration, then the sigma of x depends on the distance x. It will multiply with a, and then the zr f of x, this will be equal to sigma x, and multiply the distance become the centroid A, and this is become the centroid Y. Okay. So the whole axial stress equations. So axial stress can be written as a sigma of x equal f of x divided by a of x. So it's quite similar to what we have at the beginning, but here we did the axial stress. This is more likely to represent the functions. Okay, so it is a function of x. So the centroid is for ZR is Z, for the YR is Y. Now, to get this simplified or can be calculated easily, there will be some assumptions. So this is the assumptions that we should have. So the first assumption is the bar is prismatic. So which means that all conditions in all, I think, problem case in our course, the bar will be, it is straight and then have a same cross section. So all the things will be identical all the length. Okay? And then it's homogeneous, which means that the bar will be having the same material. Okay? The load is applied as equal and opposite uniform stress distributions over the two end cross section of the bar. So it will have the same axial loads like this one here, the same axial loads over the opposite uniform stress distribution at the two end cross sections. It will be the same or equal. Okay. So how we describe is on this picture here. So it has the axial load, same material, all the cross section has the same area. Okay. So we can distribute it all forces. They are equal or homogeneous on every surface. Okay? Every surface here. Okay? So if you cut here, it will be the same. If you cut here, it will be the same. Okay? So it's the simplification or assumptions to help our calculation. Okay. Or if we want to write here, we can write the sigma I equal Fi over Ai. This is the uniform axial stress. So basically, it will be very similar, okay? And we are going to see later on how we apply with the different subject. Okay, so that's the stress resultant. And perhaps, let's say we are going to apply to another example that is, I think, it's a very typical diagram or conditions, and sometimes in exam this will also come a lot. So we have a circular rod which is described by point A, B, and B, C. And we have two rods that we are going to, it says that it is welded. Okay, so two solid circular rods welded to plate at B. So B is a plate, and we merge these two together at this plate. Okay. to form a single rod as in this figure 1, and consider 30 kilonewton force at B. So this red is the 30 kilonewton force, and then it will be uniformly distributed. So I will just
One possibility I see is on Ting's Hao Road, Section 3 in Zhongzheng District. Is that the one you're looking for?
Okay. Siri comes just nowhere, so just ignore that. So uniformly distributed. Okay.
I couldn't find any matching places.
Okay, and then 10 kilonewton load at C to be applied at the centroid. At the centroid. So it is exactly at the middle and at the center of this circular rod. Determine the axial stress in each portion of the rod. So what does that mean? It means that since the picture gives you the diameter here, so we need to make adjustment or make observation. And simply, this is going to be the first one, we cut this one, okay? And then the second, we cut this two, okay? And see how the stress works, okay? So that's how it is. So let's say we are going to cut open, okay? So we draw the free body diagram. So if we start from 1, so let's say we start from 1, then we have, so let's say we have cutting here. Let's cut over there. So I will draw from the sides. So this is 1. Okay, and then this is 2. And it has 10 kilonewton over here, right? This is C, this is B. And then the uniform distributed on B is here, let's say here. So if we cut 1 on that distance, then we will have this reaction forces F1 or internal forces F1, right? And let's say we have the diagram for rod 2. If we cut this open here, and let's say we only have, since our external on this second member is only 10 kilonewton, then we have F2 as the internal forces. Now from these two free body diagram, so this is free body diagram parts. So in mechanics of materials, we always start with the free body diagram, okay? So we have F1 and F2, that will be the forces from each one of the member or the rod now. And since they are just a normal forces, and it is only horizontal forces that is working, so we could say that we are going to apply the sigma F for the one, for number 1, which we are going to say that the right value is the positive value. This will be equal 0. So F1 is on the left, so negative F1, negative 30 kilonewton plus 10 kilonewton. So F1 is negative 20. Okay, and then the second, let me just finish this. we still have some thing to do, but I will have a break now. Okay, now let's continue the calculations. Now, since stress defined by force divided by area, so we need to find the surface area. So surface area we could find, let's say the A1 here from the diameter 20 millimeter. We could use directly the area for the this circle, pi over 4, and this will be d1 squared. Or if you want to use radius, you can use radius, pi over 2 r squared. I will use this. So this will be pi over 4, 20 millimeters squared. And A2 this will be 15 millimeter squared. Or if we compute using the pi, I have computed here, it's around this. And then based on what we have, we can axial stress sigma 1 is F1 over A1, which we can just input negative 20 kilonewton over 314.2. This will be negative 63.7 megapascal, and F2 over A2 for sigma 2, this will be 10 this will be 56.6 MPa. Since this is a negative, this will be a compressive, this will be a tensile. So I think when we get the review or the solution, we could check back to the system. So this will be compression, this will be tension. Sigma 1 is here, which means this makes sense that this is having a compressive stress. And sigma 2 here, which we see that it is also, I think makes sense that this has this and that stress, which is going to be a tensile stress. So we have that, and this is going to be that stress, okay, compressive and tensile. Okay, that's the stress. Okay, so let's move to another subject, which is the strain. So we have stress and strain, and we are going to see how they both relate with each other. So we call this the extensional strain. Okay. So if we have a body, a solid body, which subjected, so if a solid body subjected to external load or temperature changes, the key point here is it can deform. And how it will be deformed, it can change the length, it can change the angle. Okay. For example, if we see this bar, which we have a rectangle pattern and another square which is oriented 45 degree DEF, and if we deform, if we applied some loads, external loads, so from these A conditions it becomes this. So the ABC with the asterisk is the new shape, which is more rectangular, and then the DEF also a new shape, which change the angle. It's not the same 45 degrees. And if you see the whole length, it is going to add some distance delta L. Okay, and this is new length. Now the strain within this conditions, we can make the average. Okay, we can make the average. So the we call if okay, so if the L asterisk is greater than the original L, this is we call strain, or strain using the epsilon is positive and is called tensile strain. And the opposite, if the length becomes shorter than the original, the epsilon is negative and is called the compressive. And strain is dimensionless, so it's not in specific dimension or unit. Okay, so we can say it's meter over meter, millimeter over millimeter, or inch over inch if we use the British standard. The strain itself, based on the picture, is the delta divided by the original L. Okay, I think quite okay here. So for all the chapters, throughout the chapters, we can assume, so one assumption here to simplify our calculation. So only consider case where the extensional strain is uniform along the length of a member, or simply we could just say the axial strain is the same as just delta L over L. Okay. So all the strain will be uniform. So along the bar or the member, it will be the same. Okay. There are some example which I need to discuss. Okay. So one example here is this one. Okay. So we have the rigid beam AB as we shown here as in the picture figure 1. Figure 1 is horizontal. So when the rigid beam is horizontal, the rod BC is strain free, which means it's normal. Okay, nothing happened. And then we need to determine expression for the average extensional strain in rod BC as a function of the angle theta of clockwise rotation of AB in the range of 0 to pi over 2. And then determine the approximation for epsilon that gives acceptable accuracy for values of epsilon when theta less than 1 radian. So it's quite heavy, seems, but it's not that complicated. So let's see here. So what it means is we have this angle here. okay, which determines the rotation on this AB. So the AB, it can rotate. Okay, it can rotate. And the range of rotation is from 0 to pi over 2. So it means that we can somehow just make sure that the rotation is not over the places. Okay, so this arc here, okay, which means only in the first quadrant in the other dimension. Okay, so we can write the extensional strain using this assumption. So we could just write first that the extensional strain is the L minus L over L. Okay. Since we have 3A and 4A in the sides of the, so imagine this is a triangle. So when AB is horizontal, there is nothing happen. So this is the original 5A. So the BC, the rod BC is 5A. So the L, original L, is the BC is equal 5A. And then we are going to deform the beam AB. So beam AB will rotate. Okay. So this will be rotate, and this BC will have some sort of stretching. So it has some extended length. Okay. So let's just make that happen. And this will be the how we assume our diagram. So L becomes L asterisk, adding some delta over here, right? And the B is displaced on this point, so B asterisk, okay? So of course, this is our original site, 3A. It has another additional, according to this movement, we have another C asterisk, and then the new B asterisk, okay? The B asterisk from this rotation, okay? Now, this is the theta that we assume, okay? We assume that will be a theta between 0 to pi over 2, right? So basically, by taking the Pythagorean, so we have this triangle now. So let's say this is the L asterisk. This is the B asterisk. This is 3A plus C, right? Okay, so let's say we are going to take the L as using the Pythagorean. Okay. Now, looking back on this theta, so B, if we have the theta over there, okay, so if we take the 4A as the AB, so let's just write here, this is, let me add here 4A, okay. Now we have the angle here, okay. So based on this is 4A, we can have the triangle there. We have C, 4A, theta. So we know the C asterisk you see before A, right? So we can say the C from here, C is for A sine theta, right? And B for A cosine theta, right? Okay. The sine theta is this over here, right? And then the same thing here, we get another one, right? Yeah, if here B over for A, right? Cosine theta, yeah. And then we can apply this B and C into our calculations. So let's write here that the strain is L. Or let me just write over here. So this will be 3A plus 4A sine theta squared plus 4A cosine theta squared and minus L is 5A and divided by L is 5A. So we can factorize A, right? This A squared, we can factorize and just write A. So we can write this as 3A, and then this will be 3 plus 4 sine theta squared plus 4 cosine theta squared minus 5A divided by 5A, and we can simply cancel all A like that. And this will be how we can simplify this. 3 is become 9 plus 24 sine theta plus 16 sine squared theta, and this will be plus 16 cosine squared theta minus 5A over 5A. Oh, A is gone, sorry, it's 5. And then this sine squared and plus cosine squared is both, they are gone, right? So this will be, we can write like this, right? So this will be equal to 16. So I will just erase everything here, okay? 16 plus 9 is 25. So 25 plus 24 sine theta. I will write this as divide by 5 separately, okay? So 5 I will go put inside, so it's become 25 divided 25 is 1, right? Plus 24 divided by 25 sine theta minus 1, okay? So this will be the strain with the independent variable theta. So number B, this is A, right? This is A. Number B is approximate the epsilon that gives acceptable accuracy when theta is less than 1 radian. So B, so if theta is less than 1, what will happen if the theta is really small? We can say, if you remember trigonometry, the sine theta will be equal to the theta itself. So for small values of, let's say, theta, then this, if we have this will be equal to this. This is from the it's from the mathematics, but this, I will just write here to help simplify the subject. So for theta less 1, the epsilon will be this will be equal to so divide by 2 is 12, so 12 over 25, so 24 divided by 2, 12 over 25 theta. Of course, you need to know like how this has happened. This is when this is from the binomial expression, but later, for your simplification, we can see how the small displacement for the small strain behavior it works. Okay, so I will give you another perspective on how we could also see and simply telling what kind of development in the real applications. For example, every time you work with the structure like a building, the bar, they are always in a displacement, but it is within within the safety. Like for example, this building, of course, some part of the building, because it's loads or it's withhold some external loads, that is our people here. So we will have some loads that somehow, perhaps at some certain point, it has like a small displacement. That is okay. Small displacement, that's still okay. Small displacement, that's still okay. So let me explain a little bit on what will happen. So if we have this small displacement, so for example here we have some idea on how we could simplify this to our calculations. So you see that if we have this AB, this is the left one is the actual what we see, okay, in the real world. So the rotations, it makes this going to deform, right? It's going to have a stretch, and you'll see that this is going to have like some sort of rotations like that, okay? But since the theta is really small, okay, it's really small, we could assume this is just a vertical line. Okay? We could assume this is a vertical line. This is to help our adjustment in a structure. Okay? But it is happen only when the theta is quite small. It's really, really small. Okay? So this is when theta is small. So this will be assume or approximate to be vertical. So this is what I would like to write here. Since the theta is very small, of course this is assumption, we assume this is helping the design, then epsilon also very small. And this is the normal behavior. This is normal behavior in structural engineering. And this is something that is, we say, the formations too small to be observed. For example, the strain is in, for example, order of 0.0001, for example. That's quite small, or less. I think this is also considered small, 0.001 or less. Okay. So if we applied the Pythagorean to wrote this strain, so the strain A is B asterisk L, so if we follow the actual displacement, this will be L plus displacement B squared. And taking the Pythagorean, this will be A1 minus cosine theta A squared minus L divided by L. And we have a series which we can simplify through here. This will be L squared plus 2L plus A squared and then we have a series here, 4 factorial and so on and so forth. The Maclaurin series. This is positive, minus positive, and minus 1. And we can ignore the squared term. And we can see that this strain A is basically just that. Because also in N, since the theta we can approach with sine inverse, and the delta over A we can approach using the series, then the theta A can be also approached by delta B over A. This is for the left one, so this is for strain A, okay, strain A and theta A. Let me make a little bit smaller. I need at least one space. Resize a little bit here. And this will be resize a little bit and move forward about there. And for the figure rod PC is vertical, then our strain will be directly here, which the angle is going to be, since it's vertical, since this is vertical, we can just assume this is in the tangent, okay? So tangent theta is delta over L, right? So on over A, sorry. So this will be the tangent. So delta is delta over A, okay? So we can write this is directly the tangent inverse of delta B over A, in which the delta B over A within the series is or we could say then the theta is delta B over A. So basically the conclusions is that the theta, no matter how you view the left or the right, it will be the same. So instead of going to be circular like this, we could just assume this is to be vertical, just to make sure that we can just simplify and make it into a tangent equations here. Okay. The delta using the tangent. So you could directly, if you have this kind of questions, and we could ignore everything and make sure that will be small displacement, small angle. You could assume that this works with the tangent directly. Okay. And one more thing on the strain is just this, the thermal strain. So this is just a small note. So delta T is the increase temperature increase, and then this is the thermal strain, and alpha is the coefficient of thermal expansion. So temperature increase if this is going to be positive, or decrease if this is negative. And we could imagine the block like this. Let's say we have a block which we can expand. Let's say this is Y, this is Z, this is X. So if the thermal strain happening, we could see that we could expand into all direction of this block, okay, for example. So if you have a strain, and this will be equal strain YT, this will be equal to alpha delta T. So the strain on X, Y, and Z, they will be free to expand from all to in all directions. And depends how it can expand through some length, we can just multiply with the length, or we could say the delta L for each directions. Okay, I think not really that much for the thermal strain. There are example, but I think I will just skip example. Not many questions related to thermal strain, so I will just skip that. Now I would like to just go into the brief intro on the stress strain diagrams, or the introduction to the mechanical properties of material, which I believe if you take material science before, you already have some basic knowledge on it. I will just review what it is and maybe just emphasize which part that we need to take care on, especially the mechanics property on this course. Okay, so if you see here, this is the tension testing. Both are for metals and ceramic, A, B. And if you haven't learned before, this is the specimen for the atypical tension testing. So if you are going to perform tensile test, this is how you have your material. So the materials will be in this shape. Okay, this L0 or L0 will be our actual observations here, which we can observe. If this is going to change, then we can only observe our original length on this L. Okay, and this is if the specimen deformed, we have a new length, which is L asterisk, and there will be some sort of change of shape in the specimen if we put some loads on those specimen. And this is or if you see specimen, that is based on the standards that have been designed. Usually if you are looking for a material standards, usually we are using the ASTM. That is the standard for testing. I forgot the number, but you can check ASTM for tensile test. And it will give you all the numbers you need. For example, how is the length for this one? We call the gauge length. The gauge length is the standard for the tensile. It is made specially for tensile testing. And it needs to be in this shape. If not, then tensile test is not in the standard. Okay. So that's the tensile test. And I think I will go into more details. I think next week we are going to into details for the stress strain diagrams. Tomorrow I will start the exercise, which we have the first one, and then maybe add exercise from the stress and strain. So hopefully tomorrow I can give you one more exercise from chapter 1, one more exercise from chapter 2. And if you have time, maybe another example, maybe 3 questions. But usually 2 questions will be for 1 hour. So the first 20 minutes is first question, the next 20 or 30 minutes is the second question. Okay? And yeah, I think that will be all. And before we end, okay, let me